everybody. My name is Beniamin Drasovean, and as Mihai said, I'm a software engineer at MultiversX. Since I joined the firm back in 2018, I've been working alongside the protocol team on the state part of the blockchain. That is why today I want to talk to you about scaling blockchain state. When I say state, I mean the way we store and manage accounts, smart contract code, smart contract storage, and account storage. State is a bottleneck for every blockchain architecture. And that is why without improving the state, your blockchain won't be able to grow. This is a short summary of what I'm about to talk to you about today. So first, I'm going to explain to you how our state works, how things are right now. After that, I'm going to tell you about some big improvements that are going to come in the next release called Sirius. And after that, some future steps, things that are in research and things that we are thinking about implementing or already started implemented. So let's start. The foundation of our state is the Patricia Merkle tree. This is actually not the Patricia Merkle tree. It's a simple binary Merkle tree. But for the simplicity of things, I have chosen this image. And there are a few keywords that you need to know to understand this. So first things, we have leaf nodes. Those on the bottom, labeled with L, L1, L2, L3, and 4 are leaf nodes. And those leaf nodes are used to store data. So if you create an account on our blockchain, your account will be stored on one of the leaf nodes. All the other nodes are called intermediary nodes or branch nodes. And there's one special node, the one from the top, that is called a root node. And why do I say that that node is special? Because that node, or the hash of that node, summarizes the whole tree. Let's take an example. So in this image, let's say we have 4 accounts. They are stored on the leaf nodes. Our account is labeled L3. If you send a transaction from that account, your balance will change. That means that the hash of the account will change. The parent node contains the hash of the child node. So also the hash of the parent node will change, and so on until the root node. So the root hash will actually change. For each small change in any of the leaf nodes, the root hash will change. And the tree we are using is actually not a binary tree, as I have already said, but each parent can have 16 children because we use hex strings for saving accounts and smart contract codes and stuff into the tree. If you ever read our white paper, you could see that we have state sharding. That means that the state is split between shards. So if you create an account, that account won't be present in each of the shards, but in only one shard. You can send transaction to any account, so that's not a problem. You can send transaction across shard, but each account or each smart contract code deployed, it's only stored in one shard. Furthermore, for each shard, we have a main tree, and the main tree stores accounts and smart contract codes and multiple data trees. So you store an account, the account is stored on the leaf of the main tree. If you unmarshal that account, that data structure has a field named root hash, and that's the root hash of the data tree, which holds the storage data for that account. So each shard has one main tree, multiple data trees, which holds the storage for the accounts and smart contract storage. And there's one special tree and that is present only on the meta chain, and that's the peer tree. The peer tree holds information about the validator nodes from the network. There are some state operations, operations which we do with our states. The first one is state sync. If you ever started a node on our blockchain, you could see probably before in the first messages, tree is syncing. That means that before your node can execute transactions, you need to hold the whole state for that specific shard. So you have to sync it. What you need to know is just the root hash of the main tree. You ask your peer nodes, okay, give me the node which is related to this root hash, and they will give you the node. After you unmarshal that node, you can check the hashes of the children and request the children nodes, and so on until you sync the main tree. For the data trees, when you receive a leaf node, you unmarshal it, and if there's a root hash set for that account, that means that account has a data tree, and you have to sync that data tree also. The next operation is called in-epoch pruning. Every version of your account is saved into storage. So if you execute a transaction, your account will change, and that version will also be saved into storage, and so on and so on. So you can imagine the state will grow continuously. Way we have found to combat this is called in-epoch pruning. We don't actually need all the history of your account, because we cannot refer it before the final block. So we can remove all the state that was modified before the final block. And we had that since we launched the mainnet. So we had that from the beginning. A small problem with this is that it's using a bit more RAM and a bit more CPU. So we have found another way which helped us remove unwanted state, which is called storage pruning. That means that in each epoch, you create a new database. And you save the current state in that epoch's database. Let's take an example. It will be a bit simpler to understand. So you create an account in epoch 2. That account will be saved in the database of epoch 2. When you go to epoch 3, you create a new database. And when you go to epoch 4, you create a new database, and so on. But there's a problem here. You created your account in epoch 2, and you didn't change anything in that account. That means when you go to epoch 3, your account will still be stored in epoch 2. When you go to epoch 4 and 5 and so on, your account will be still only in epoch 2. And storage pruning means that when you reach when you have more than 4 open storers, you remove the one older than 4 epochs. So if you are in epoch 7, your database for epoch 2 will be removed. So your account will be removed. And the node will not be able to load that account, so it will go to jail. Snapshot means that at the start of each epoch, you copy the current state to the new epoch. So you created your account in epoch 2. When you go to epoch 3, your account is still part of the current state. So you copy it to epoch 3. Then you copy it to epoch 4. Then to epoch 5, to epoch 6. When you go to epoch 7, you can safely remove the database for epoch 2, because your account will be in epoch 7, 6, and so on. That was the first part of my presentation. Now the improvements we have made for the serious release. We have here an unbalanced data tree. And the feature is called auto-balancing data trees. Yeah, do you see the leaf node down there? In order to reach that leaf node, when you want to load the data that it contains, you have to load all the intermediary nodes. So it will take a lot of time. This is possible because for the data trees, you can specify the key at which it will be saved. So at the key that you specify, that key will be used to store the data in the tree. If you use data with prefixes, you can have something like that. So in order to combat this, we have come with a feature that instead of saving things at the key that you provide, it will save the things at the hash of the key. And that ensures us that we have a random distribution of the nodes. So the trees will be balanced. When this feature will be activated, all the leaves that are modified will be saved with a new version. So instead of saving the leaf of the key, it will be saved at the hash of the key. We have run some benchmarks for this feature. And if we migrate the whole state, and we have already implemented a built-in function that we can call, which migrates all data to the new version, the state will be reduced by 11 million tree nodes. So you can see that the state access will be much faster. The deepest data tree, which right now is 43 levels, it will be only 8 levels after the migration. The next feature is called dynamic gas cost for data tree loads. The gas cost must be related to the time it takes to execute a transaction. So if you load the data, a leaf node, until now we had a static gas cost. It didn't matter that you loaded that leaf node from the 3rd level or from the 10th level. but the time it takes to load the leaf from the third level is a lot less than it takes to load it from the 10th level. So it was not really accurate, the guess cost with the time it takes to execute something. We have benchmarked the time it takes to load the leaf node from level 0, 1, 2, and so on, until level 50. And you can see the results with the green line on this graphic. After that, we have the quadratic polynomial, which approximates this function. So in that quadratic polynomial, if you replace x with the depth from which you load that tree node, the leaf node, you will get the guess cost. The guess cost for loading that leaf. This will be available in the next release. Some other big improvements coming in the serious release. Self-healing ability. Right now, if you have a hardware problem and one tree node is not saved into storage, when you want to access that, you won't be able to because you don't have it. So your node will go to jail. Your validator will go to jail. In the next release, we added self-healing ability. When you try to load a tree node that is not present because of a hardware problem or something, you can sync that from the network directly. So your state will heal itself, and your validator will be able to execute transaction continuously. Another improvement we have found is using sharded persister for each database, and the get function is 3 times faster, and the put is 4 times faster. Another one is we have found an improvement for syncing. Right now, if you start a node on the shard 1, it will take about an hour and a half to sync the whole state for shard 1. After this improvement, it will take like an hour and 5 to 10 minutes. So it's a 20% sync time improvements. And how we achieve this is by synchronizing data trees and the main tree in parallel. So you synchronize the main tree, you reach a leaf node, you unmarshal that leaf node, you see that it has a root hash, then it means it has a data tree. You can start syncing that data tree in parallel. And by doing this, we have a 20% sync improvement. These are the features that are coming in the next release. And the third part of this presentation, I said I will tell you about our next steps, the things that we are researching or already started implementing. The first thing, support for light clients. We are thinking about implementing light clients, and that means we have to do some changes on the state part. This we have already done. We need, for light clients to work, we need to collect state changes for each transaction. So we have already done this. Each transaction has some state changes. We collect this and send them to the light clients. And the light clients won't need to have the whole state, just the state changes, and they can see that the transaction was executed correctly or not. Another feature we are working on, archive unused state. So if you deploy the smart contract in Epoch 2, for example, and you didn't use it since then, because of the snapshot, that smart contract code will be copied to Epoch 3, to Epoch 4, to Epoch 5, and so on. But if the smart contract is not used, you can archive it, and that means that the smart contract code will be moved from that storage to a static storage. You won't be able to access it, but it won't be removed. If you want to access it after that, you can send a built-in, you can call a built-in function which will unarchive that state. And another direction we are researching, we want to implement Merkle trees. This will help with Merkle proofs. Merkle proofs in this case. Merkle proofs are a lot more smaller and easier to compute than Merkle proofs. So what I want you to remember after this presentation, the serious release will reduce state sync time, will improve state access time, and will have a self-healing ability in case of any issues. And as you have seen, we already have some improvements for the next releases. Thank you for your attention.